This topic is of great interest, and we have to track it because back in about 2010, a paper came out written by two climate scientists actually claiming that a wet bulb temperature of 35 degrees C would basically become deadly for humans because that's when the thermoregulation of the human body tends to shut off or fail, and then the body is unable to get rid of the heat via sweating and so on, because sweating is a cooling mechanism, and if the air is saturated with humidity, then the body cannot get rid of heat by evaporative cooling of the sweat. But since then there's been a lot of debate about where this limit actually is. This adds a little bit more detail with some experiments that we will look at. It's a long paper, very nice long discussion as well, and very nice experiments with statistically significant results, findings, which sets new limits. So it says validating new limits for human thermoregulation. One thing is clear, that you don't have to wait till you hit the limit of survivability. Many bad things happen even before that, like exacerbating existing conditions, COPD and cardiovascular diseases and diabetes even, and many other things. And it's of course age dependent, and gender also matters, and of course there are vulnerabilities that are also related to where you live, how you live, per capita income, healthcare, and so on. So let's read the most salient points, and I picked those for you, but if you are interested in more, you obviously need to read the paper. It's a very nice paper, appeared in the Proceedings of the National Academies of Sciences in the US just literally a few weeks ago. I'm recording this in June 2025. Significance of this study then: research blending climate models with physiological data has projected that large geographical areas may soon experience heat stress exceeding human limits for thermoregulation. Model thermoregulatory limits were derived from laboratory research using thermal step protocols. You can go and read what that means. Despite the growing popularity of this technique, its principal assumption that core temperature inflection during stepped increases in heat or humidity demarcates thermoregulatory upper limits has not been validated. So results have been reported, but in actual real world settings and with humans, this has to be validated. By exposing participants for 9 hours to conditions just above or below the core temperature inflection point, we found that thermal step protocols effectively identify the conditions above which thermoregulation is impossible. So inflection point is basically where beyond that threshold the system is going to fail, right? Our findings provide critical support for heat stress projections incorporating empirical tolerance limits, because climate models are now beginning to worry more and more about this thermoregulation and trying to look for the places where this is going to be exceeded and how soon, etc. And then there is the whole debate about whether 1.5 degrees C will make it impossible for many regions in the world to survive, or 2 degrees C, and so on. And then there is the other aspect where you can use the atmospheric dynamics to say what are the constraints in the deep tropic or tropical regions, for example, to reach that thermoregulation critical threshold or inflection point. I have a podcast on that you can look up. Okay, all these things matter because we do need to keep an eye on where and when we are going to hit these limits. So we also provide data characterizing physiological strain during prolonged uncompensable heat exposure. You know what that means. So that's the significant statement meant for the non-experts. For the experts, there is the abstract, of course. Recent projections suggest that large geographical areas will soon experience heat and humidity exceeding limits for human thermoregulation. The survivability limits modeled in that research were based on laboratory studies suggesting that humans cannot effectively thermoregulate in wet bulb temperatures TWB above 26 to 31 degrees C, values considerably lower than the widely publicized theoretical threshold of 35 degrees C. Okay, that's a serious drop in the threshold, and we will hit that very quickly in many places with continued warming and continued increased greenhouse gases, of course. The newly proposed empirical limits were derived from the TW corresponding to the core temperature inflection point in participants exposed to stepped increases in air temperature or relative humidity in a climate controlled chamber. So you're not gradually increasing then sustaining it, you are just jumping the temperatures and humidities. Despite the increasing use of these thermal step protocols, their validity has not been established. We used the humidity step protocol to estimate the TW threshold for core temperature inflection in 12 volunteers to determine whether this threshold truly demarcates the TW above which thermoregulation is impossible. Each participant was subsequently exposed to TW above 33.7 degrees C and above. It's called T above, and it's in excess of 33.7 degrees C, and below 30.9 degrees C, which is considered T below in their acronyms. Their respective inflection point 32.3 degrees C for up to 9 hours in random order. So it's a real experiment designed very well for the range of temperatures for thermoregulation and the inflection or failure of the thermoregulation system. Obviously, human subjects are involved, so they would have taken care of all the details. Core temperature rose continuously in T above. It was projected that core temperatures associated with heat stroke of 40.2 degrees C would occur within 10 hours. While T below was also uncompensable, the core temperature rate of rise was considerably lower than in T above, such that it would take more than 24 hours to reach 40.2 degrees C. You see 40.2 and somehow you jump to 42. It's kind of a brain wire to do that. Our study supports thermal step protocols as an effective technique for evaluating survivability limits for heat exposure and provides a direct assessment of the limits of human thermoregulation. Okay, so obviously there are other factors such as age and gender, as we said. Whether a fan is running can make a difference as well in terms of the time it would take for you to get a heat stroke and so on, right? Just to read off some of the front material setting the theme, tolerating prolonged exposures to high temperatures is primarily dependent on the ability of the thermoregulatory system to maintain body core temperature within the relatively narrow limits required for normal physiological function. We are endotherms. In heat exposed persons, heat gain from the environment and metabolism initially exceeds the rate of skin environmental heat loss through sweating, or you can increase the sweat evaporation by having fans, or of course AC is not going to give you a heat stroke if the AC is working. So heat gain from the environment metabolism also initially exceed the rate of skin environment heat loss, which causes heat to be stored within the body and its temperature to rise, and then you're going to get a heat stroke. Elevated body temperatures trigger autonomically mediated elevations in skin blood flow and sweating to facilitate heat dissipation via dry and evaporative mechanisms. So radiation and convection also works. If your skin gets very hot, the air above will warm and it will take away the heat, and sweating and skin blood flow increase until the rate of heat gain is compensated by heat loss and body temperature stabilizes. That's the thermoregulation. If, however, the achievable rate of heat dissipation is insufficient to offset heat gain, conditions are uncompensable and body core temperature rises unchecked. How long an exposed individual can survive uncompensable heat exposure is determined by the magnitude of the disparity between heat gain and the maximum achievable rate of heat loss. So you can look up the definition. So I will leave it there and just jump to some material ahead. Participant characteristics, obviously they have taken an average year of 28, which is fairly young, if they are also healthy, because they would have probably chosen healthy individuals to make such an intervention of 9 hours of heat exposure. Sex, both of course, females 3%, males 9% out of the sample. Sorry, 3 and 9, 12 individuals, 25% and 75%. Height, body mass, you can take these as health parameters that will matter, but also tells you that the experiment gives you a small section of the population that is exposed to validate these empirical numbers of inflection or heat thermoregulation failure, right? So diabetes, diastolic blood pressure and systolic blood pressure are supposed to be in the range of, you don't want to expose somebody who has high blood pressure to such an experiment anyway. So study protocol for an example participant, there is relative humidity, there is esophageal temperature, and there is relative humidity and exposure times. So obviously there are stepped exposures as we mentioned, and relative humidity you can see here below estimated compensability limit of 30.7 TW, which is called T below in the paper, and T above where you have humidity step estimated compensability limit in the middle with 33.5 degrees C wet bulb temperature, so 42 degrees C with 56% relative humidity. Okay, so you know what wet bulb temperature is. The thermometer just measures the temperature, but if you put a wet cloth around it, then the temperature it corresponds to the wet bulb temperature, because if you evaporate the water vapor to achieve that relative humidity, then that would give you wet bulb temperature, okay, or the condensation in this case. So if there is humidity, no, you have a wet cloth, so he will evaporate to the limit of the environment in which you are, the relative humidity, and you will cool the wet bulb, right? So just think about it. Rectal temperature responses to above and below inflection conditions. So basically we are now getting into specific numbers. So these are exposure hours above compensability limit. So you have rectal temperatures here rising continuously as there is a bit of cooling here because the body is trying to compensate, and then you are going to rise uncompensably. Let's say when you are below compensability limit, you don't rise uncompensably. There is a flattening because thermoregulation is still working. And here is the control sample at 17.7 degree wet bulb, and you can see it's relatively flat. So body is very good at regulating healthy young individuals. And exposure rate of change in rectal temperatures. So rectal temperature change T above in this range degree C per hour of change, and here you have T below, so you are obviously in the well below range here, but this is the T below 30.9 degrees C, and this is the control, which is this one, which is not increasing at all, it's around 0, and the Kaplan-Meier curves for participant withdrawal during exposure. So people begin to say this is not going to be compensable for me, or the discomfort, etc., right? So distribution of bootstrap estimates for projected time to heat stroke with sustained exposure. You don't want to take people to the limits of heat stroke, so you have to do some estimates. So this is the proportion of bootstrap estimates above estimated wet bulb limit. Is very short here in terms of projected time to heat stroke, but between condition difference and between below estimated wet bulb temp limit, So there are long tails. I won't go into the details here, but you get the idea of what the experiment is trying to do. It's taken the published estimates of thermoregulation inflection points and trying to validate them through these well-controlled, well-designed experiments. End exposure rate of rise in mean skin temperature and heat rate. I hope so skin temperature change in degrees C per hour for T above, T below, and control. So again, same story. And you have, so the zero line is here. End exposure rate of change in heart rate. So obviously you want to measure all parameters to see the heat. So skin temperature change is important because then it tells you how sensible and convective and heat are being removed by the body to compensate thermoregulation and when it can fail, right? And it comes through heart rate change as well, of course, right? This is another figure, physiological responses to heat exposure, rectal temperature after 9 hours of exposure. You can see again how the uncontrolled rise above for T above works. In T below you are still regulating, but it's not as cool as the 17.7 degrees C with 56% humidity. Heart rate at 9 hours of exposure. Some more details. Whole body sweat rate, obviously higher here, but still not able to regulate the temperature. Lower, but in the range of thermoregulation, not failing or below inflection point. Control is, of course, you are comfortably sitting there. Sweat rate is near zero. Okay. Mean skin temperature after 9 hours. Again, similar story. Okay. All these are important medical factors. And let's read the discussion and implications. It's a bit long, but I have taken the whole text, and let's see if we need to read the whole thing. A humidity step protocol effectively identified the TW above which thermoregulation is not possible for humans, and this you want to map at a very hyperlocal scale so that across the globe you know which places are going to hit this limit at what time. 1.5 and 2 degrees C are fine, but honestly we just need to know at every location with each 0.1 degree warming where are we heading in terms of TW or thermoregulation limits. In conditions hotter than the estimated TW limit for the thermoregulatory compensability, the body temperatures and heart rates of exposed volunteers rose rapidly and unabated. By the way, they call wet bulb temperature as TWB, whereas we generally use TW, so I'm going to just leave it as TW, just because saying TWB versus wet bulb temperature, which is shorter. While writing, TWB saves a lot of space, but while reading, TW is easier. I don't know why I'm explaining that to you, but anyway, it was projected that core temperature associated with heat stroke, which is at 40.2 degrees C, would occur within 10 hours of sustained exposure. You can quibble about whether this is different for different people, but obviously they looked at healthy young individuals and males and females combined, but obviously you want to be very careful well before you reach this temperature, because this is going to be different for pregnant women, elderly people, young people, and so on. Our study validates the central assumption of thermal step protocols. In doing so, we also provide critical support for recent research coupling empirically estimated compensability limits and climate modeling to project how climate change will impact global exposures to uncompensable heat stress. Not only is the planet getting hotter and more humid, the safety margin between experienced heat extremes and the limits of human heat tolerance is thinner than previously thought. So 35 degrees centigrade wet bulb temperature was thrown up as the limit, but obviously we are well below that. The upper limit for thermoregulatory compensability occurred at a wet bulb temperature of 32 degrees C. So 42 degrees C air temperature with 51% relative humidity in our participants. At this time, at this same air temperature, the limit estimated in the PSU heat, Penn State University heat study under the minimal physical activity condition was 27 degrees C wet bulb temperature, so that's 42 degrees C air temperature with 40% relative humidity. Obviously it's hot and humid outside and you are working outside or running around exercising or doing whatever it is, you are going to reach the threshold of your thermoregulation much quicker. The discrepancy, so that's where heart rates also come in. The discrepancy between these values likely stems from our participants being exposed at rest, and so there are some differences. I won't bother with it. Our data also fall within the range of temperatures in which compensability is not possible for resting persons. What do you want to know? People who are working outside and what is their limit, or people who are resting? For older people it may be more about resting. For kids it may be about not playing outside when it's hot and humid, and pregnant women resting, and so on. So it's a complicated thing, but having just a broad range of human thermoregulation inflection point can help us monitor things. Then heat action plans come into play, early warnings are needed, and so on. So rather than estimating survivability limits empirically like thermal step protocols, biophysical models employ mathematical equations describing body environment heat exchange with key inputs derived from laboratory studies. So they are still empirical models but built on data from experiments. So these rational models allow for rapid evaluation of how variations in ambient temperature, ambient conditions, or other factors such as personal characteristics, heat interventions, responses reduce your risk. Obvious, right? How they modify limits for thermoregulation. However, model outputs are highly sensitive to the choice of limits, and based on our finding that thermal step protocols provide a valid estimation of the limits. While exposure to TW above the core temperature inflection point was uncompensable, our data are less clear as to whether conditions were compensable just below this threshold. Body temperatures and heart rate increased progressively in T below 30.7 degrees C or whatever we looked at. However, the rate of rise in this condition was considerably slower than in T above. We looked at the plots already, and so that would require more than 24 hours for heat stroke to happen. We don't want to find out anyway. A potential explanation is the short step length, so that's about the rate at which you change the temperature and humidity. A potential explanation is the short step length employed, 5 to 10 minutes. Heat gained at the skin is transferred to the body core through convective exchange via the blood and conduction between adjacent tissues. So there are some details on how thermoregulation actually works. So it takes 4 to 6 hours for stable core temperature to be re-established in resting persons moved from thermoneutral to simulated heat wave conditions. So there is a recovery time as well. Once you are exposed, if you don't die, then body still has to recover if your core temperature has gone up. So a delay of this magnitude is unlikely to be relevant for thermal step protocols. So it's more about how experiments need to be designed. Our findings support the thermal step protocols as an effective method. As we said, estimated empirical limits for research employing thermal step protocols should be used further to expand climate modeling to a wider range of populations. So now that we are sure this is the results from this protocol are experiments with this protocol are reliable, we can begin to include them more broadly into climate modeling and projections, and of course risk maps. Estimated compensability limits for older adults who are at elevated risk of heat stroke and other heat related injuries due to age related declines in thermoregulatory function are available but have yet to be incorporated into climate models. Work is also needed to determine compensability limits in other at-risk groups and so on. Future research and modeling should also consider that even in compensable conditions, prolonged heat exposures can increase physiological strain and the risk of numerous adverse health effects. So assumptions about core temperatures remain at near basal levels until conditions become uncompensable is a common assumption, but this assumption may stem at least in part from typical development of hypothermia observed during thermal step protocols, whereby core temperature is initially stable until the compensability limit is exceeded, and then it just takes off. However, a potentially concerning physiological heat strain can be experienced in conditions below core temperature inflection, even though it was projected that it would take more than 24 hours of sustained exposure for heat stroke to develop. In the T below or 30.9 degrees C wet bulb temperature experiment, core temperature and heart rate were still elevated by 0.9 degrees C and 41 beats per minute from the control conditions after 9 hours of exposure. So multiple factors, it's not just temperature and humidity, it's the length of exposure and then additional physiological factors like age, gender, etc. Right? So moreover, clinically meaningful elevations in thermal and cardiovascular strain leading to reduced autonomic function and adverse symptoms have been observed in older adults during prolonged but compensable exposure to wet bulb temperatures as low as 22 to 26 degrees C. So this is very important because there is the survivability limit and inflection point, but where do which age groups begin to have real serious risk factors, right? So I don't know if I want to read all these details, but wow, that's a lot of text I have put in here. Okay, the primary limit. So just jump ahead. Let's read what the limitations are. The primary limitation of our study was that due to the time and resource-intensive nature of conducting day-long exposures in climate-controlled chambers, we were only able to directly validate the central assumption of the thermal step protocols under a single atmospheric temperature relative humidity combinations. So you need to do much more of those. All that is required for our finding to generalize to different ambient conditions and populations is that the relationship between the core temperature inflection and the limit of thermoregulatory compensability is not altered in the other contexts that you can look at. So these results still remain very valid for generalizing to include in climate models and risk warnings and so on. Okay, so such research can be used to refine climate health projections, but also direct measurements of physiological responses and their associated uncertainty in uncompensable conditions could be used to refine for biophysical models. So as we go forward and the warming continues, at least in most places, we must track these things. So depending on how rich a society, community, a nation is, Singapore worries a lot about personal heat tolerance. I think Sweden and mid-latitude countries also worry about it because oddly, the strong wet bulb temperature exceedances happen in the subtropics where there is sinking, as opposed to tropical regions where there are some dynamics that limit these things. Without, I have a podcast on that elsewhere. So in general, for poor and developing countries, you still want to have a very good sense of the risks and how quickly we are heading towards survivability limits in those countries at a very local scale. You need to know this at a very local scale. So by exposing participants to conditions just above and just below the thermal step protocol estimated core temperature inflection point, we demonstrated that this technique accurately identified the limits of human thermoregulation. Our findings support thermal step protocols as an effective and, given their short duration, efficient as well in terms of the methods for evaluating the limits of human thermoregulation. Expanding estimated tolerance limits to a greater number of populations and contexts and subsequent incorporation into climate models is needed to further the development of health-centric warming projections and adaptation strategies for protecting heat vulnerability groups. So there are two time scales worrying about where we are headed in the coming years and decades in each location, but also what can be done right now with early warnings and heat action plans, cooling centers, shelters, hydration, but how do you deal with old people who may not have resources or workers outside? And there are lots of heat adaptation literature. There is a lot of heat adaptation literature as well, which I have covered in other podcasts that you can look up. Okay, so let's leave this here for now.